next chapter is going to take a look at applications of the derivative in the real world. And a lot of those applications build on what we know about the first and second derivative in relationship to their graph. So let's first start talking about the first derivative. And the graph. We'll start out with a picture. Let's say I've got some curve here. And let's take a look at the derivative here at this point on the right. Remember, the derivative is the slope of the tangent line. And you notice that tangent line has a positive slope. It's going uphill. And the graph is also increasing, going up from left to right. So we will say if the derivative is positive, that means the graph is increasing. If I were to take a look at this point over here in the middle, you notice the tangent line there is going downhill because the graph is going down. So here the derivative is negative. That means we have a decreasing graph. Another point of interest might be over here at this valley. You notice the tangent line there is flat. There, the derivative is 0. And it's not increasing or decreasing down there. It's actually the minimum of the graph. And there's another spot that has a derivative of 0. That's at that local maximum, that high point of the graph. And that's what happens when the derivative is 0. It means we have either a local minimum or a local maximum at that point. It's not always a local minimum or maximum. Sometimes it's what we call a saddle point. And a saddle point is when the graph comes up, levels off, and comes back up. And yes, the derivative will be 0 at that point as well. And it's not a minimum or a maximum because it's still increasing or still decreasing at that point. But generally, we're going to find for this class, it means we have a local minimum or maximum when the derivative is 0, which means when the derivative is 0, we're very interested in that point. We call it a critical point. That's where the derivative is 0. Technically, the derivative could be undefined as well at a critical point. But for our course, we're going to focus on when that derivative is 0. Because if the derivative is 0, it could be, not necessarily, but it is a candidate for a local minimum or a local maximum. So for example, if I had the function f of x equals negative 2x cubed minus 3x squared plus 36x plus 17, if we want to know where these critical points are, the potential minimum and maximum points, we can take the derivative of the function, which would be negative 6x squared minus 6x plus 36. And then we can set it equal to 0, which we can solve by factoring. First, I'll factor out the negative 6, giving us x squared plus x minus 6. And then it's going to be x plus 3 times x minus 2, which means we can see our critical points are when x equals negative 3 and 2. Those are our critical points. Those are the values for where we might have a minimum or a maximum. So how do we decide if it's a minimum or maximum? We need to know whether these regions are increasing or decreasing. To help us see where it's increasing and decreasing, we're going to make a little number line here with the critical points of negative 3 and 2 on it. And then we're going to decide if the derivative is positive or negative to the left in the middle, and to the right. We're going to take this factored form of the derivative, the negative 6 times x plus 3 times x minus 2 equals 0. And we're going to see what happens with each of the critical points, or the regions from the critical points. When x is less than negative 3, what happens? When x is between negative 3 and 2, what happens? And when x is bigger than 2, what happens? And we don't really care about the number as much as we care about the sign of each factor. So the negative 6 is just a negative number. And if I take a number that's smaller than negative 3, maybe negative 4 plus 3, the answer will be a negative. So I care that the answer is negative. And if I take a number smaller than negative 3, like negative 4, and subtract 2, it's going to be even more negative, which means we have a negative times a negative times a negative, which is a negative. Because the derivative is negative, we know in this region left of negative 3, the graph is decreasing, going down. Between negative 3 and 2, then, the negative 6 factor is always negative. And then if I pick a number between negative 3 and between negative 3 and 2, maybe 0. 0 plus 3 is a positive. And 0 minus 2 is going to be a negative. And so I have a negative times a positive times a negative, which is a positive. Because the derivative is positive, I know the graph is increasing after negative 3. Then if I pick a number bigger than 2, the negative 6 is always negative. Number bigger than 2 might be like 10. 10 plus 3 is a positive. And 10 minus 2 is also a positive, which means we have a negative times a positive, which is a negative, which means the graph is going down. It is decreasing there. We can summarize that in interval notation. The graph is decreasing. Thinking about, we've got negative infinity on the left and positive infinity on the right, decreasing from negative infinity to negative 3. Then there's a gap. We'll represent that with a union. And then it's decreasing again from 2 to infinity. Where's the graph increasing? Well, that's in the middle. That's from the negative 3 to the 2. And since we can look at this and see that there is a valley down here at negative 3, this is going to be the local minimum of the graph. And because there is a peak up here at the positive 2, we can tell that's going to be a maximum value, a local maximum on the graph. So we kind of get this idea that the graph is going to come down, increase, and then come back down, where we've got negative 3 is the minimum, and positive 2 is the x-coordinate of the maximum. We're getting an idea of what the graph looks like. Now, this example alternated between decreasing, increasing, and decreasing. I want to warn you that that does not always happen. We need to beware of saddle points that kind of throw a curveball into the graph. Let's say I've got a graph here that's going to come up, level off, come up, and then come down. Maybe that level off happens at 1, and that bend to come down might happen at 3. There's going to be 2 points where the derivative is 0, which means when we make our sign chart with 1 and 3 as those critical points, you'll notice when we go to the left of 1, you're going to find out the graph is increasing. We're going to have a positive derivative. But between 1 and 3, we also have a positive derivative, because the graph is still increasing before it bends down and starts to decrease. So here in this example, we're increasing from negative infinity up to 1. And then we'll say union, because we have to jump over the number 1, because at 1 it was actually flat. It saddled off. So we'll go union 1 to 3, and then say the graph is decreasing from that 3 up to infinity. So even though there are 2 critical points in this example, only one of them is actually a maximum, and the other is a saddle point. All right. The first derivative told us whether or not the graph was increasing or decreasing. The second derivative is going to give us even more information about the graph, and that is the topic of our next video.